Well, the coefficient of x2 is minus 3 over 2, so we'll be dividing by minus 3 over 2, so that's the same as multiplying by minus 2 over 3. And we'll have minus 5 minus a half, so that's plus a half, times x3, which is 1. So that's 5.5. So minus 5 plus 1 is minus 4.5. Times by minus 2 is 9 divided by 3. That's going to give me 3. X1 is the last one. The coefficient of x1 is 4, so we're going to divide by 4. We've got 18 minus 9 times whatever x2 was. Okay, so 9 times x2 minus 1, so that's plus 1 times x3. So 18 minus 27, that's minus 9, plus 1 is minus 8, divided by 4 is minus 2. Okay, and so that's the solution to that problem, to that system using LU factorization with partial pivoting. Right. Excuse me. Right. Okay, so I'm just going to stop sharing my screen for a sec. If I can find where are my commands. Okay. Does that just a bit of a pause in proceedings? Does that make sense in terms of LUP factor? I say LUP, LU decomposition with partial pivoting. Do you feel you'll be able to do one yourself? Nobody going to say? Okay, I'll continue on if no one else objects. I say no one else objects. No one has objected yet, but I'll just continue on. Don't worry about that. Okay, so that's LU factorization. Now, LU factorization is used quite often especially with implicit Runge-Kutta methods. So with an implicit Runge-Kutta method, there's usually a linear systems to solve to calculate the stage values. Okay, so that's why we use LU factorization. So it is a very common method. It isn't the most efficient method. Sometimes there are more efficient ones, and that's what we're going to be looking at now. So I'm just going to share the screen again, and this is lecture notes. Okay, so hopefully you can see a lecture note, a page that says Cholesky decomposition. Now, this is a form, or it's a similar form of decomposition as what we just looked at, but this is very efficient and can be used when we have a matrix, which is what we call positive definite. Okay, Anne-Marie, we've got a question. Is a P matrix only used for creating the new B in order to create the Y matrix? That's correct. Okay, so if I scroll back up to the Krauss method with partial pivoting, yeah, so you're applying the partial pivoting to A. You then calculate LU based on A, and then because you've swapped, because this is essentially this is A after the row swaps, because we swapped those rows, we have to also swap the rows in B. Okay, so it's only required in the solution for Y. Okay, we don't have to do it again. Yeah, that's a good question. Yeah, yeah. So moving on to Cholesky decomposition. So this is when we have a matrix in a certain form, which is called a positive definite matrix, and the definition of a positive definite matrix is it's a symmetric matrix. Yeah, it's a symmetric matrix, which means there's kind of a line of symmetry about the main diagonal. It's said to be positive definite if for any vector x, so x is any vector, if x transpose A times x is positive for all for a non-zero column vector x. Positive. Okay. There is another way to check whether you've got a positive definite matrix, is if you've got a symmetric matrix which has all positive eigenvalues. Okay, so that's another way to check. So if we do have a positive definite matrix, we can calculate what's called Cholesky decomposition. and it's similar to LU in the fact that we want to factorize our matrix A into the product of two matrices. But with Cholesky decomposition, it's the two matrices are the L, which is a lower triangular matrix, and L transpose, which, if we transpose a lower triangular matrix, is an upper triangular matrix. Okay, so L is our lower triangular matrix, and we multiply it by its own transpose, we should get A. Okay, so let's have a look at a 3 by 3 example. Okay, so there's my lower triangular matrix, this 3 by 3 example, and there's L transposed. Okay, so carefully note that these subscripts here are slightly different from what they usually are, because so we've got L21, L31 on the first column, that becomes the first row. So if I multiply these two together, I get this. Note that this is symmetric. So for example, this element here in the second row first column is the same as the element in the first row second column. So what this means is I only have to calculate one triangular region, so the main diagonal elements and the lower triangular region, and I know the others. So in this 3 by 3 matrix, I've got 6 unknowns. Okay, so rather than in the 3 by 3 LU factorization, I had 9. In the Cholesky decomposition, I've only got 6, so it's more computationally efficient. But of course, it only works for when we have what's called a positive definite matrix. Okay, so for certain applications, now quite often positive definite matrices do pop up. They pop up in sort of statistics and also in other forms of ODE work as well. So they are. So it is. If you identify you've got a positive definite matrix, Cholesky decomposition is more efficient. So if we look at the elements on the main diagonal, okay, they follow a pattern, and the pattern is we have. Let's take when I is 2, so we've got Lii squared plus L21 squared. And when I is 3, we've got L33 squared plus L32 squared plus L31 squared. Okay, so this is that pattern. So the main diagonal elements follow this pattern. For all other diagonals, sorry, for all other elements, they follow this pattern. Okay, so we can rearrange these to give us this equation 6.3. So this is for calculating an element of our matrix L. Now, if we're on the main diagonal, we have this first case, and for all elements below the main diagonal, we have this case. Okay, so Cholesky decomposition can be quite tricky. We do have an additional, subscripts in. Okay, so I just noticed something. Yes, I've just noticed something here. Okay, I don't know whether that's the same in your one, but that should be a K. So that's summation there, where it says J equals 1 to I minus 1. That should be a K. Okay, so I'll correct that for the PDF on the notes. Okay. Right, so let's have a look at the Cholesky decomposition of this matrix. It's a K in our book. Okay, for some reason in my one I've got it as a J. That's good news. So the following matrix, this is Bethany says yours is a J. I don't know how that's happened, so my apologies for that. So just make sure it's checked whether that is a K. This A, I'm going to tell you straight away, it's a positive definite matrix. For any exercise I give you or a question I give you about Cholesky decomposition, you can assume, but it's positive definite unless I ask you to show, but it is. Okay, so you can see this is symmetric. So for example, that -2 there is the same as that -2, that -4 is the same as that one, etc. And if we calculate the eigenvalues of this, it should be all positive. And what we do is we look at the same as before, columns of A. So first column, L11 is equal to the square root of AII, so that'll be A11, and this summation here doesn't exist yet, okay, because J is equal to 1, so that doesn't exist. So it's just a root of A11, so that's just root 4 equals 2. L21 Okay, so now we do this. So 1 over L JJ, so that'll be 1 over L11. And again, this summation doesn't exist yet. So 1 gives us -1. And similar for A31. So 1 over the L11 multiplied by A31. Okay, so that's the first column done. Onto the second column. And remember, we're only looking for the lower triangular elements, so we're not going to bother with L12 because we've already calculated L21. So we know that L12 is going to be -1, although it's a lower triangular matrix anyway. So we go straight to L22, which is the first case. So we have the root of A22 minus L21 squared. So this time J is equal to 2, so K is 1. So that gives us 3. And L32, we use the second case. Okay, so we plug those values in and we get a 1. So we've only got 2 lower triangular elements to calculate on column 2. On the final column, we've only got 1, which is this element here, L33. So L33 is using the first case. So we have A33 minus L31 squared minus L32 squared. And we've already calculated those, and this gives us 3. So our L matrix is here. Okay, so we only had to calculate 6 values as opposed to 9 for LU factorization. And if we check that L times L transpose is equal to A, you can see if we multiply these two together, we get A. Okay, so that's Cholesky decomposition. Very useful because it cuts down on the amount of work we have to do. Here's a code. I'm not going to spend too much talking about this. It's just sort of some standard code. So loop through the columns, calculate the main diagonal element. Okay, so this for loop here calculates our sum, and then we square root or subtract the sum away from AJJ and then find the square root, and that's the lower triangular ones as well. So I'm not going to focus too much about that. By the way, MATLAB does have Cholesky factorization built in. It's Chol, so CHOL is the command. So if you put L equals Chol and in brackets A, or your A matrix, that will do the same thing. Okay, and this example here is just showing you, but it works. Okay. Now, so the Cholesky-Kraut method. So this is the Kraut method, which is applied to Cholesky factorization. So remember, we're solving a linear system of the form AX equals B, where A is positive definite. Okay, so we calculate Cholesky factorization. So instead of A, we've got L times L transpose. So if we let Y equals L transpose times X, we solve for Ly equals B, which is the same as the first step in the standard Kraut method. Okay, so L is a lower triangular, so this is solved using forward substitution. And then we solve for L transpose X equals Y using back substitution. Okay, so we only need to calculate that one matrix L. So here's the example in the notes. Same coefficient matrix as we just used, but here we've got some a constant vector. Okay, so we first solve for Ly equals B. So using forward substitution. This time our main diagonal elements may not be 1. Okay, so we do have, so we might have to divide. It's not as simple for the first one as in LU factorization. Okay, so for example, 2y1 is equal to -2, so obviously y1 is -1. See, for forward substitution, we get our y values, and then we use L transpose X equals our y values we just calculated, and we calculate that using back substitution. Okay, and I've got some code below it. So what I'm going to do now is actually have a look at another worked example. So this is in the exercises at the back of the chapter. Okay, so I'm going to look at exercise 3A. And what all of these are actually positive definite matrices. Okay, so there's not going to be any trick questions involved in this one. Okay, so I'm just going to share my other application. Okay, so that's my what I'm going to do is just hide that, and here's what I prepared earlier. Yeah, I've already. Yeah, that's still J as well. Okay, yeah, I'll have to look into that, why that became a K. Oops. Okay, so what I'm going to look at is the just going to bring up the question. Okay, so this is question this is 3A in the exercise. So I'm just going to write down what the coefficient matrix is. You will notice also as you go through these exercises, I have chosen quite nice values, and that's deliberate. Okay, it's not obviously in practical real life you're not going to get nice values, but for these exercises I've chosen deliberately nice values, because if not you end up with loads of square roots when doing Cholesky factorization. And we've got minus 30. So this is what we're going to solve this using Cholesky. Right. So first L11. So this is the first case, and because I is 1, we don't have any summation, so that's just going to be root of our A11. So our L11 is going to be 4. Okay, L21, which is using the second case, so that's going to be 1 over L11 multiplied by A21. So it's 1/4 times 16, which is also 4. And similar for L31. So 1 over L11, A31. It's 1/4 times 4 is 1. Okay. Change the colour just because I'm getting bored of that colour. Right, so now we've done the first column. So moving on to the second column. Okay, I don't bother with this element, so I'll go straight to L22. So L22 is back to the first case, but we have one term within our summation. So we've got A22 minus LJK. Okay, so LJK. So J is 2 and K is just 1. So it's L21 squared. So it's going to be A22 is 25. L21 is 4. So that's 25 minus 16 is root 9, which gives us 3. Okay, and we've got L32, and that's going to be the second case. Okay, so that's going to be 1 over L22. I'm going to have A32 minus, so we're going to have L31, L21. So L31, because I is 3, K is 1, and J is 2, so that's going to be L21. So you have to sort of keep track of the subscript. So of course that should be a K. Right, so L22 was 3, so that's 1 over 3. A32 was 10 minus L31, which is 1, multiplied by L21, which is 4. So 10 minus 4 is 6, divided by 3 is 2. So you can see these are nice numbers coming out. Actually, I use a different colour. Okay, go on for next column, L33. So it's just 1 to calculate. So that's going to be a square root of A33. It's meant to be a 3 minus L31 squared minus L2 squared. Okay, so it's going to be root of 6 minus 1 squared minus 2 squared. So 6 minus 5 is 4. Square root of 4 is 2. Okay, so our L matrix is going to be 4, 4, 1. So that's the first column. 0, 3, 2, the second column, and 0, 0, 2. Okay, so if I multiplied that by the transpose of itself, I would get the original matrix up there. Okay, so we're solving that system. So step 1, let's have a different colour. Step 1 is solve for L y equals b. So 4, 0, 0, 4, 3, 0, 1, 2, 2. Is L3 3 right? Yeah, that's a good point. Best to actually get it right before conceding. Indeed, it is the root of 1. You're right. So 6 minus 1 minus 4 is what? Root 1. Thank you for that. Okay. Always like to keep you on your toes. So B was minus 8, minus 47, and minus 30. Okay, so Y1 is going to be a quarter of minus 8, so it's going to be minus 2. Y2 is going to be, well, the coefficient of Y2 is 3, so that's minus a third, minus 47, minus 4 lots of Y1. Quite a lot of minuses here. So that's going to be 47 minus 47 plus minus 47 plus 8. That's going to be minus 39 divided by 3 is minus 13. I was worried then. I thought it was going to give me a nasty number. And Y3 is the coefficient of Y3 is 2, so that's going to be 1/2 minus 30 minus 1 times Y1, which is plus 2, and minus 2 times Y2, which is plus 26. Running out of space a wee bit, but minus 30 plus 2 is minus 28, plus so that's going to be minus 1. Oh, minus 1 or minus 2? Oh, it's going to be, because I forgot to change that, didn't I? If I just rub that out for a sec. So that was 1. So that shouldn't be just 1/1. So minus 30 plus 28 is minus 2. Okay, that was the first step. On to the second step. Yeah, thanks, Sophie. Yeah. On to the second step. So we have L transpose. So the second step is L transpose X equals Y. So transpose of this 4, 4, 1, 0, 3, 2, 0, 0, 1 times x1, x2, and x3. And this is our right hand value, so we've got minus 2, minus 13, and minus 2. Okay, so that one we did forward, this one we're going to do back. Okay, so x3 is going to be equal to minus 2. Okay, so 1x3 is minus 2. Here we're going to have 3x2 plus 2x3 is equal to minus 13. So we're going to have 1/3 minus 13 minus 2 times x3. So minus 13 plus 4 is minus 9, divided by 3 is minus 3. And finally, x1 is equal to, so x1, so the coefficient of x1 is 1, making it easier. So we have minus 2 minus 4 lots of minus 3. Oh, hang on, coefficient of x1 is 4. I got carried away then. I thought it was going to be easier than that. Got 1/4 because of that coefficient of x1 is minus 2 minus 4 lots of x2 minus 1 lot of x1. Okay, so -2 plus 12 is 10, plus 2 is 12, divided by 4 is 3. Okay, so that's our solution. Okay, yeah, so x3 is -2, x2 is -3, and x1 is 3. So that's a solution used in Cholesky decomposition. It's easier. I say it's easier. There's fewer. I should use proper grammar. There are fewer L values to calculate than LU factorization. You could use LU factorization on this. That's, you know, give you the same result, but this is more efficient. So if you can identify, if you've got a positive definite matrix, it's much more efficient to do Cholesky decomposition than LU. Okay. Right. Are there any questions about LU? Oh, sorry, LU factorization or Cholesky factorization? I mean, how have you found that? You'll notice as I've gone through a couple of worked examples, there's a lot of writing involved. Okay, there's a lot of writing, there's a lot of almost repetition of writing out most of these, but it's important you to do it by hand using a pen and paper, because when we come to program a computer to do what we want, it's important we know exactly what we're expecting and what the steps are. Okay, so that's what I wanted to cover with you for today. We do have some more time left. Is there anything you would like me to have a look at? And also, are there any questions about all of the previous chapters which we've done so far? Okay, so that's a question. So question 3B on the assignment. I'm really glad you asked that. Right, so yeah, so question 3B, this is all about solving a system of ODEs. Now, a lot of the examples I've shown you in the notes are all about solving a single ODE. So what I'm going to do is just bring up the lecture notes again. Okay, so I'm just going to go back to, I'm actually going to go back to the first chapter, and we've got solving higher order ordinary differential equations. Now, I say hidden away. Down here, there is an example of solving a system of ODEs. Now, in the coursework, I'm asking you to solve the SIRD system. So that's a system of 4 equations. Okay, so the number of equations you have doesn't matter. You could have 10, you could have 100. The program is still the same. Okay, so this is going back to, I think this is on page 7 of the lecture notes. Okay, so this is example 1.5. Here we have a system of 2 equations. Okay, 2 ODEs. Now, when you have systems, we write it using vectors. Okay, so we have a vector of y value, so that's the left-hand side of our system. So we call y as y1 and y2, and you have f. I call it big F for the vector, and that's the right-hand side of this. So this is of the vector y. Okay, so the right-hand side is y2 minus y1, and our method is just applied to the vectors themselves. Okay, if we scroll down, you can see this is the Euler method for solving a system of equations. Now, the change is this bit here. Okay, if we had a single ODE, we wouldn't require the comma and then a colon. But in our case, we have a system of ODEs. So, and I've defined the system here. Okay, what I think I'd do is I'll bring up MATLAB and I'll show you a different example. Right, so what I'm going to do is just bring in MATLAB. and bring in a new live script. So I'm going to go through an example of using MATLAB or using ODEs to solve a linear system. Okay, can you see a MATLAB live script? And is this big enough for you to see? Just to clarify that. Okay. Right. First thing I'm doing, I'm going to clear, and I'm going to define an ODE. So define the ODE function. So same thing as or before. Normally we'd have something like that. So if you're solving a single ODE, it's just t plus y. If you have a system of ODEs, what is best to do is output a vector. And so the vector I'm going to output is going to be y2, and then I'm going to output 9.81 times sine of t. No, sine of y1. Okay, there's a particular ODE system I got in mind, and this is of a pendulum. So if you imagine a pendulum, okay, swinging back and forth, this is the ODE that models that. So 9.81, some of you may know as the acceleration due to gravity, and I think that should be minus 9.81 because it's acting towards the ground. So this will model a pendulum. Y1 is the angle but the pendulum makes with the vertical. Okay, so it doesn't really matter, that's a system. For yours, you would have something like, okay, at ty, okay, y would be s, I, r, and d. Okay, so y would have 4 values in it. So so you might have something, I can't quite remember if it's something like yeah, you'd also have beta, gamma, and mu. Okay, so without sort of showing you too much of the solution, so your system would be a system of t and y, but you'd also have those parameters beta, gamma, nu, and you'd have n. So actually, if I bring in the coursework, I'll show you what I mean there. Okay, so I'm just going to switch across to a different application. Okay, so this is the system you're asked to solve, S, I, R, and D. So those are your 4 equations. So your y vector would have 4 elements. So y1 would be S, y2 would be I, y3 would be R, and y4 would be D. Okay, and your right hand side, okay, so you'd have minus beta is over n, beta is over n minus gamma I minus mu I, for example. So instead of I, that would be y2. Instead of s, that will be y1. Okay, so that's the first thing you have to realize. Okay, so our parameters b, mu, what we got b, gamma, mu, and n. They also have to go in your function declaration. So let's have a look at have I made a syntax error in the code? Just go back to. All right, so let's have a look at that. Yeah, that should have been like that. Yeah, because y is going to be a multi. It's an array of multiple values. Okay, so yours, you'd have ty, and if it's the first one, without giving too much of the game away, the first one it would be minus beta times, well, it'll be I times s over n. But if your y array was s, I, r, and d, okay, y is the same as y2, and s is the same as y1. Okay, so that will be your first element within your function output. Okay, so we need these additional variables into your function because later on in the question in part C, in part 2, you're asked to experiment on different values of beta. So you need that beta in there. Okay, so back to I'm going to go back to what I'm doing here. Okay, I'm going to define some initial values for this. Let's go for, say, 10 seconds. So I'm going to T-span. I'm going to model this pendulum for 10 seconds. Y0, what I'm going to do is, this is obviously your initial state of the system. So in this pendulum problem, I'm going to say it's angle 1 radian away from the vertical, and in this particular system, the second element is the rate of change of that angle. So at the beginning, that angle is stationary. In the assignment, if I just bring in the assignment again. In the assignment, you're given what the current state of the system is. So there's a population of 5 million. So without giving the game away, you'll need to use something as equal to 5 million. Initially, 10,000 people are infected. So your Y component in that array, your initial infected will be 10,000. Current rate of infection is 0.4. And so beta is the rate of infection. Those who recover from the disease do so after 21 days. Okay, so the rate of recovery, if it takes 21 days to recover, that'll be 1/21. Okay, so gamma. So if you recover after 21 days, gamma is 1/21. And the mortality rate, which is mu, is 2 in 1,000. So that's 2 divided by 1,000. So you know what n is? N is 5 million. Your initial infected is 10,000. So if your initial infected is 10,000, susceptible would be how much is in your population minus the number is initially infected. And we're assuming that nobody has recovered or died yet. Okay, so we don't have information of recovered or died, so we set those equal to 0. So your initial state of the system will be S, will be N minus 10,000. N is 5 million. I is 10,000. R is 0. D is 0. Okay. Beta is 0.4. Gamma is 1 divided by 21. And mu is 2 divided by 1,000. Okay, so that's your initial system. So if I go back to the example I was looking at, go back to MATLAB. So you would have 4 numbers there. I've just got 2. Okay, set a step length. Notice in the question I haven't asked for a particular step length. I don't really mind. It doesn't matter what you do, but obviously it's got to be stable. Okay, so it's up to you what step length you use. It's not a stiff problem. I'll give the game away now. It's not particularly stiff, so it doesn't really matter. Okay, what I'm going to do is code up for this one. I'm going to code up the second order Runge-Kutta method. Now we're dealing with arrays. Okay, so instead of a single equation, I've got 2 equations. So what I'm going to say is my first row is going to be y0. Okay, so every row of y is going to be the state of my system at a particular value of t. So before, if we had a single ODE, we just have that. But because we've got a system of ODEs, I'm going to say the first row is equal to 0, 1. T, for example, time, well, that's just a single element, a single variable, so that's going to be T-span 1. Okay, how many steps have I got? So I've got number of steps is T-span 2 minus T-span 1 divided by h. Okay, so that will give me the number of steps. Okay, so in this case I've got 100. That makes sense because I'm going from 0 to 10 in steps of 0.1. Okay, so then we do the loop. So this, I'm going to use a second order Runge-Kutta method. I think you're asked to use your explicit Runge-Kutta method you derived in the earlier part. So if we calculate stage values, so this will be f of Tn and f of Yn. If we were just dealing with one equation, that would be sufficient, but we're dealing with a system of equations, so I have to use the whole nth row. Okay, so K1 now is going to be a 1×2 array, and K2 for this particular Runge-Kutta method, it's f plus h and yn. So remember, instead of yn, I've got the whole row of y plus h times k1. Oops, forgot the times. Okay, so those are my stage values. I want to update my solution. So again, if we were dealing with a single ODE, we just have yn plus 1, but because we're dealing with a system, we use the comma colon. So remember, this is all about array slicing. Okay, so that would be a current row of y plus h over 2. So this is the second order Runge-Kutta. Okay, so that's so Sophie asked, what would the value of h be in your coursework? I don't mind, whatever works. Okay, you're dealing with quite a large t-span. So the t-span, if I'm just looking in, you're dealing with 100 days. So your value for your t would be number of days. So t1 would be 1 day. So h1 would mean you'll be updating daily. It's not a stiff system, so it doesn't really matter. If you used h of say 10, it probably wouldn't work. You wouldn't get very good results. So I'll leave that up to you to decide what you want your h value to be. Okay. So going back to the code, increment t by h. Okay, let's just see. I'm going to press run on that, see if it works. It's not shouted at me. It's not giving me any scary red values. I'm going to leave it at that. So let's plot the solution. So if I plot t against y, okay, you'll see I have 2 lines. Now this is because if I just output y, okay, you can see y is a 101×2 array. Okay, so the first column is y1, which was here. First column is y1, which was remember that was the angle of my pendulum. The second column is the rate of change of that angle. So the first column here is my angle in radians. The second column is my rate of change. So it would be useful to have a legend here. So if I do legend, if I say theta, I say theta, that's angle. Yeah, I say theta is the angle of my, and I'm going to call it d theta. It's a change in the angle. Okay, so the blue line, that is the angle. So imagine a pendulum going backwards and forwards. Actually, I'll just sketch that for you. Just going to, I might as well share my whole desktop because I keep going between various applications here. So what I mean by in this particular example, okay, imagine a pendulum. That's the vertical, so that's an angle theta. Okay, so this pendulum will just oscillate backwards and forwards. So it'll go that way, that way, that way, that way. Keep going. Okay, so theta is the angle, and d theta, which is the rate of change, that's the first derivative of theta, is the rate of change. And because gravity acts down on it, that's to do the my system in this one was something like this. It was g times sine theta 1. Okay, that's the equation of a pendulum. So I only picked that one because it's an example of a 2. It's a 2 system. Okay, so in yours, if you were just to plot t against y, you'd have your number of susceptible, number of infected, number of recovered, number of deceased on the same set of axes, which, if I recall from the question, so just bringing in the question, produce a plot showing the number of susceptible, infected, recovered and deceased on the same set of axes. So that's quite easy to do. That's just plot your t against your y vector, and that will give you all your plots on one. Okay. If you wanted just one of those, so let's say in my example, I just wanted the first. I just wanted the angle for my theta. I would just plot. Oh, hang on, sorry, that's a totally wrong one. I'd put the first column. Okay, so each column of y is a separate variable. So this is my angle for my pendulum. So you can see it just oscillates between 1 and -1 as it sort of swings backwards and forwards. To answer your question earlier, Sophie, about step length, let's say if I use a big step length of 1/2, in this particular case it's gone unstable. So what if I had 0.2? Okay, oh, that's gone unstable as well. So I haven't done any stability analysis of this, but as you can see, I've just experimented with H, and H value of 0.2 means this is going unstable. So if I stick a H value of 0.1, you can see it's stable. Oh, actually, I'm going to say it's stable. It's starting to pop over. So this kind of thing is what you'll need to do. It's what we call a numerical experimentation. Okay, so as I reduce the step length, I get a better better solution. So this code here, this is a Runge-Kutta method for a system of ODEs. So the key thing is here, wherever you got y, we have to use the nth or n+1th row. So we do that by putting comma colon after it. Okay, and we also, with our y array, in this case we've only got 2 elements, or 2 columns in y. For the assignment, we'd have a column each for S, I, R, and D. Okay, does that shed a bit more light on it? So if you look at the Euler method code at the end of the chapter 1, at the end of chapter 1, or have a look at what I've done here. This is for a second order Runge-Kutta method. So for a 4th order, you'd have K3 and K4, and whatever your values of A, B's, and C's are for that. Okay, does that shed a bit more light? I mean, are there any questions about that coursework? One thing I would suggest is, and by all means, you're free to do this, it's not cheating, is actually look at the SIRD model. Okay, so if it jumps the SIRD model, you can see what's a typical type. That's a typical type of solution you should expect. Okay, so this is a plot of. That's a bit sort of. Yeah. Okay. See. Oh, this is an interesting one because it's actually showing the different values of beta. Okay, so this is a typical behavior of an SIRD model. So you can see the blues are susceptible, orange infected, etc. And in this particular one, they're changing the value of beta, and look what's happening to the peak infected. So that gives you a little bit of a hint for the question. So that was, you can see I just did a quick Google search, and I think it was Wikipedia. That gives you a quick hint on this part here. Now, I don't mind how you do this bit. I haven't got a particular set. There are various methods you can use. I'm interested to see what you come up with. So how do you find what's the target infection rate so that the number of infections does not go more than 2 million. Okay. Right. Almost to the end of this session now. Does anybody have any other questions? Okay, yeah, so lots of people have been struggling with question 3 part A. Right, So MATLAB gives you empty sum errors. I don't know what's changed. Can't get any. Are there any tips you can give the question at all? What I would say, it's partly a problem with MATLAB. MATLAB solvers aren't brilliant for symbolics, but it will give you. I mean, this is, I use MATLAB. That's how I actually calculated this. There are a number of order conditions. I think it's chapter or part section 2.4 in the notes. Those order conditions are the order conditions for a fourth order Runge-Kutta method. If I go to the notes. Okay, so we're looking at a fourth order Runge-Kutta method, and here are the order conditions. And I think there's an example here. Okay, if you'd have just copied and pasted or copied out this example, I think most of you have found, but it does give you 0 values. The reason for that is because it's overdetermined for particular values. Now, if you don't use all of these equations, so equations 1 to 11, if you can see in this example, I've used them all. If you don't use all of them, you've got to select a few. You can solve for the values. A tip is solve for the b values first. And what I mean by that is I clumped them all into one. So I said, I kind of, just for brevity, I said, okay, solve all of those. But for the b values, okay, so as you can see there, we have 4 order conditions for the b values. Now, how many b values are you given, and how many b values do you need to solve for? So what you can do is you can split the problem up. You could just solve for the b values because you're given the c values. Once you've got the b values, then you can solve for the others. Okay, so that's kind of a tip there. It's not unique. Okay, there may be, yeah, so there may be other, I mean, there may be other fourth order ERK methods which have these values for C2, C3, C4 and B2. There may be other fourth order methods. I'm not sure whether there are or not, but there may be. You'll know if you've got a valid fourth order method from part 2. So when you look at the stability function, you'll be able to tell whether it's a valid fourth order method. Okay, if let's say by sort of the end of next week, or you're still really struggling on part 3A, what I'd recommend you do is just use any fourth order Runge-Kutta method. Okay, so because you still need to do the remaining parts of the question. Look at the marks. There are 16 marks for applying your method. So don't, if you really can't do that, don't worry about those 6 marks. It's more important that you get these 16 marks here. That's a very good, interesting question. So Irina said, if a different answer to part A, how will that affect part B? Well, in terms of the order, let's say I have an order for Runge-Kutta method and you have a different fourth order Runge-Kutta method. The solutions to part B are going to be infinitesimally different. It's going to be so close it will just be computational rounding, which means they'll be different. Because if they're both of the same order, the behavior of the errors is exactly the same. The errors will be different, but over a very minute amount, the behavior of the errors will be exactly the same. So that's a good observation there. By the way, I'm not interested, if you notice, in part B, I'm only asking for plots of your solution. Okay, so I'm not going to compare your solutions to what I've got, because you might be using a different value for H. You might be, there might be slightly different values. I'm looking at the plot of your solution. When it comes to determining that target, the target infection rate, that should be very similar. Okay. I haven't seen many questions on part 4. I assume that's. Have anybody managed to do part 4 yet, or question 4? Yeah, some of it. Okay, so the derivation of the Radol 1A method. So remember, you've got to determine how many stages a fifth order Radol method has. Okay, I'm not going to tell you that, but you've got to determine how many stages you need. Set CS equals to 1, and then you find the roots of the Legendre polynomial, PS minus 1, is it plus? I can't remember, but it's given in the notes. And you can use MATLAB to solve for those order conditions. Stability function for this, it's a determinant over another determinant. Again, the equation is given in the notes for the stability function of an IRK method. You've got to determine whether it's astable. In this one, okay, part C, okay, I want you to write a MATLAB or Python. By the way, it's I imagine most of you or all of you will use MATLAB. Calculate a solution to this initial value problem. Okay. Again, this is a second order ODE. You'll have to split it into 2 first order ODEs. Okay, so then going back to what we looked at here, you'll have something similar. So you've got a system of ODEs, not just a single one. And lastly, just before we sign off, I'm aware of the time. If we go to implicit gutter method, there's some code to help you there. So this is for what one's this, for example, 3.6. So on page 36, there's example code, and this was for this IRK method. A little hint, and this is a little hint. Look at the look at your A matrix in this method. Okay, that will give you a little bit of hint about any improvements you can make on the code in the notes. If you use the code in the notes and you adapt it for a system, for this system, that'll be fine. But there is a way of improving on this code in the notes. Okay, so here we have this code in the notes. So you can use this, adapt it. So these values, this is a value for B1 and B2, and this is A11, etc. So you'll have to change that for this method. But have a look at the A matrix there. It's a particular type of an IRK method, and you can make some stability saving. You can make some efficiency savings by how you calculate this, and that's about as much as I'll say about that. Right, so I think that's the time up now. Any final questions? Won't be your last opportunity to ask questions. Yeah. I'm just reading that from Amrita. Yeah, you can add the program. So it's useful if you upload your programs along with your submission, as Leader has suggested, because that means we can run your program. So if there's something which we think slightly off, we can look into it and we can award you marks based on what you've done, rather than sort of losing you more marks, so to speak. Yeah, so adding an actual program in a separate zip file is a good idea. Yeah, and also you can copy and paste your code into your Word or LaTeX file as well, and put it in some appendices. Okay, I'm just going to stop recording. So all of what I spoke about